Hi everyone, my name is Claire Tomlin. I'm a professor of electrical engineering and computer sciences at Berkeley, and this is the 23rd module in a series that we're recording to support the course EECS 221A, Linear System Theory. So in previous modules, we've been talking about the solution to the linear time invariant system, which involves computing the matrix exponential e to the a t, where a is an n by n matrix. And so we're used to exponential functions, but we're not, this concept of a matrix exponential, where this is an n by n matrix, and how we compute it is through the inverse Laplace transform of Si minus A inverse, again, for this n by n matrix A. So this can be a hard computation, as we talked about. And so we're going to spend a little bit of time talking about how to simplify this computation. And one of the ways in which we try to do this is to simplify the matrix A to get it into a simple canonical form where it's much easier to do this calculation. And the canonical form that we typically simplify it to is called the Jordan form, or in the case in which there are n linearly independent eigenvectors of the matrix A, that simplifies to a diagonal form. So let's start by talking about eigenvalues and eigenvectors, which is going to be our basis for this transformation to either the diagonal form or the Jordan form. So eigenvalues and eigenvectors of the matrix A. Let's assume that A is a matrix in R, n by n. And we define an eigenvector-eigenvalue pair of the matrix A as follows. So EI, which in general is a complex vector in Cn, is said to be an eigenvector, of A with associated eigenvalue lambda I, which can be a complex number, so it's a complex scalar, if the following condition holds. A EI is equal to lambda I EI. Okay, and we assume in this that EI is not equal to 0. So let's just write that here. So that's not equal to the 0 vector. Of course, the eigenvalue could be 0. So this is interesting. If we just look at this equation, this is an n by n matrix. This is an n by 1 vector. And now we have a scalar and an n by 1 vector. So if we look at this sort of amazing fact that all the information about that n by n matrix has collapsed when we post-multiply it by this vector EI into this eigenvalue and eigenvector pair. So I mean, here we have an n by n matrix, and this is only a 1 by 1 scalar. Okay, so that's interesting. How do we solve for the eigenvalues and eigenvectors? Well, if we just look at that formulation, we can see that these lambda i's, so the lambda i's are solutions to, and we'll just bring the lambda I EI pair onto the other side and write it out as determinant of Si minus A is equal to 0. Okay, so I've done a couple of steps there. I've brought this over. I've assumed that if there's going to be a non-trivial eigenvector in the null space of A minus lambda I, then I need to have that the determinant of A minus lambda I is equal to 0, or rewritten as determinant of Si minus A is equal to 0. Okay, so solving this for S gives us the eigenvalues of the matrix A. Okay, so now we can say a few things about that. So if we have a matrix A, which is an n by n matrix, then we can solve for these eigenvalues, and we find that an n by n matrix could have n possibly complex, so a real matrix could have n possibly complex eigenvalues. So in general, we could rewrite this formulation here. Let's just keep that on the board. This is actually, it's got a name. It's called the characteristic polynomial of the matrix A. So we use the terminology chi hat A of S to be the characteristic polynomial. It's just defined as the determinant of Si minus A. And in general, we can write that as, in terms of its expansion, S minus lambda 1, S minus lambda 2, up to S minus lambda n. Okay, good. So we have a formulation for the eigenvalues, how to solve them, and the eigenvectors. So the eigenvectors, once we have the eigenvalues, we can solve for the eigenvectors just by looking at the null space. What's in the null space of A minus lambda I for each index I? Okay, so we have the following interesting result now. Given this n by n matrix A, and given its eigenvalues and eigenvectors, we can say the following. That, so this is a theorem. If A, so it's a real n by n matrix, has n distinct, meaning different from each other, eigenvalues, and we'll call them lambda 1, lambda 2, up to lambda n. So they can be possibly complex, as we know, but they're different from each other. Then there exists, so the theorem states that there exist n linearly independent eigenvectors. So we can write that as follows. Then the set E1, E2, so this set of vectors, which are the eigenvectors associated to those eigenvalues, forms a basis for Rn. Okay, so basically we're saying that those, there's n of them, we're saying that they're linearly independent when we say they form a basis for Rn. And the proof of that is pretty easy. We just write it out. We write out what the result of having n distinct eigenvalues of the matrix A is. Okay, so we can prove it by saying, suppose we have n distinct eigenvalues, but now suppose these are not linearly independent, and we can derive a contradiction. Okay, so if the set EI, let's just write it as that, for I equals 1 up to n, is not linearly independent, then we can write out some linear combination of them such that the coefficients are not all 0, yet the overall linear combination equates to 0. So that we can say there exists some scalars which are possibly complex such that alpha 1 E1 plus alpha 2 E2 plus alpha n En is equal to 0, yet the alpha i's don't necessarily have to be 0. So at least one of those alpha i's is not 0, such that at least one of the alpha i's is not 0. Okay, and then we can go on. So let's just assume, without loss of generality, that it's alpha 1 that's not 0. So without loss of generality, we'll assume that alpha 1 is not equal to 0. Okay, so what does that mean? If we take this equation here, let's call that equation star, and let's pre-multiply that equation by the following matrix. So pre-multiply the equation star by A minus lambda 2i, A minus lambda 3i, all the way up to A minus lambda ni. And so we're going to pre-multiply this equation here. So the summation from I equals 1 to n of alpha I ei. So that's equal to 0. So this is equal to 0. And so each time what we're going to do is bring, so if you think about this pre-multiplication, we're going to bring the eigenvectors back into this term of matrices, and we can use the fact that these are eigenvectors to reduce each of these terms to scalars. Okay, so if we think about that successive multiplication, then we see that we quickly get that alpha 1 times lambda 1 minus lambda 2 times lambda 1 minus lambda 3, all the way down to lambda 1 minus lambda n, E1 is equal to 0. Okay, so that just resulted from pre-multiplying this equation by this factor here. And now we can derive the contradiction because we know that E1 is not equal to 0. It's an eigenvector of the matrix A. And we've assumed that these eigenvalues are all distinct. So each of these terms is non-zero. And so we derive the contradiction that alpha 1 must be equal to 0. But we assumed that it was not 0. So here we have that this implies that alpha 1 is equal to 0, which leads to a contradiction. Okay, so that tells us that if we have distinct eigenvalues, all of these eigenvalues are different from each other, then A has n linearly independent eigenvectors. Okay, so that's really important when we start thinking about the diagonalization of a matrix. But we'll do that in the next module. But at the end of this module, I'd just like to give you a little bit of an intuitive or geometric interpretation of what eigenvalues and eigenvectors really mean. And so I said that it's sort of amazing when you think about an eigenvalue that all the information about the matrix A is contained. When you post-multiply that matrix A by the eigenvector EI, you get that information about A, or the properties of A, are just collapsed into that scalar value. Okay, so we can think about relating this back to our linear systems interpretation. So we have a matrix A. It's got its eigenvalues and eigenvectors. Now let's think about just the linear time invariant system without input. X dot is equal to AX. We know what the solution to this looks like. We've spent a lot of time on that now. So we know the solution just looks like e to the a t. Let's assume that t0 is equal to 0 without loss of generality, times the initial state x0. Okay, so suppose you had an initial state x0, which was some linear combination, or let's just write it this way. It's actually some scalar. So I'll call this some scalar, but it could be a function of time, times the eigenvector EI. Okay, so that's one of the eigenvectors of the matrix A. Well, if you have that, then you can see the following, that so now this is a scalar, so if we plug this into this equation here, we'll get e to the at times the eigenvector EI. Okay, so what's that? Remember, EI is an eigenvector of the matrix A. So e to the at times EI. Let's just think about the expansion of e to the at. So that's I plus at plus a squared t squared over 2 factorial times EI. Okay, so now let's bring EI in and multiply everything here. So we get that's equal to EI plus ATEI, which is just lambda I EI t plus, and then a squared. So a squared EI, if we think about that, that's a times AEI, which is lambda I A EI, which is just lambda I squared EI, etc. So we can simplify this by basically bringing the EI in and collapsing that matrix A. So here we get lambda I squared over 2 factorial t squared, etc., which is equal to e to the lambda I t, just our standard exponential function where this is a scalar post-multiplied by EI. Okay, so that tells us that if we use this as an initial condition, then x of t is equal to e to the lambda I t times EI, and then we've post-multiplied by this scalar function. So that's just a scalar which affects the magnitude of this. So in general, if you have an initial condition, which is a linear combination of the eigenvectors of the matrix A, then you can see that you can write out the solution in terms of a linear combination of these terms here. These are called the modes of the system, related to the individual eigenvalues of the matrix A. Okay, so generalize this initial condition now to a linear combination of those eigenvectors. Okay, so geometric interpretation, well, if lambda I is real, so let's just go back to the case where our initial condition is one of the eigenvectors of the matrix A. If lambda I is real, then it says that if you start on that eigenvector EI, you're always going to stay on that eigenvector. So you start out at some point on that eigenvector, then the system will stay on that eigenvector, evolving that way or that way, depending on the nature of the eigenvalue, whether it's positive or negative. Okay, so if you start out on an eigenvector, you're always going to stay on an eigenvector. You start out on a linear combination of eigenvectors, which if we've just shown that the eigenvectors form a basis for Rn, if the eigenvalues are distinct, then you'll stay in a linear combination of those eigenvectors, and you can actually compute the terms in terms of the eigenvectors. And so you can generalize now to suppose that you start out, so suppose you consider this formulation where lambda I is now complex. So you're starting out on one of the complex eigenvalues, and the associated eigenvectors are going to be complex. So then you can show that your solution is going to stay within a linear, in the space spanned by a linear combination of that eigenvector and its complex conjugate. So that's a neat extension of what we've just written here for the case in which lambda I is complex. Okay, so what we've talked about in this module, we've introduced, so motivated by the fact that we'd like to simplify the matrix A in some way. And by that I mean we're going to perform a similarity transform on the matrix A to make the computation of e to the AT easier. We've started to think about how to simplify this or perform the similarity transform by defining the eigenvalues and the eigenvectors of the matrix A. And in the next module, we're going to use that for constructing this similarity transform. Thanks very much.